Hello! In this video, we'll cover Python fundamentals for structural engineers, variables, printing, comments, basic data types, and expressions. We'll conclude with a practical example of designing an RC sections reinforcement. First, download the notebook from the course GitHub repository. Let's start with variables. Variables are used to store information in memory. A variable has a name and stores a value of a particular data type, such as a number or text, so you can reuse it later. A variable is created by assigning a value to a name using the equals operator. For example, here we assign the value 10 to a variable named beamLength. Add a print statement in the following line and then execute the cell to display the value. You can also assign multiple variables in one line like beamLength, elastic modulus E, and second moment of area I. Just separate them with commas. Notice that if I later assign beamLength equals 8, the old value is overwritten. The first number 10 printed under the cell refers to line 4 when its value was 10. The second number, 8, refers to line 10, where beamLength value became 8. Variables can change as your code runs. When naming variables, there are a few rules. Names can only contain letters, numbers, and underscores. They must start with a letter or underscore, not a number. No spaces allowed. Use underscores or camel case to separate words. I recommend using descriptive names like beamLength. It makes your code much easier to follow. Python is case sensitive, so whether you use upper or lowercase makes a difference. Now, let's look at printing. I want to cover it early on as I use printing in every cell. We use the print function to display messages or variable values to the screen. There are several ways to do this, but I'll show you the two I use most often in my engineering work. First, basic printing. You can print a variable directly by placing it inside parentheses. For example, if I have a variable beamLength set to 8 meters, I can simply print it out this way. But usually, you'll want a more descriptive output and display some extra text like variable name or units. You can print multiple values by separating them with commas. Text values can be included by wrapping them in quotes. For instance, you might print length equals followed by comma and the beam length variable, and even add units like meters after comma. However, using many commas can become clunky. So my preferred approach is the F string. Start your string with the letter F before the opening quote. Then type your text and embed variables directly inside curly brackets at any point in the string. This lets you create clean, readable outputs like this all in one go. You can also control how numbers are displayed using this format: value, dot, precision, type, where precision is the number of digits after the decimal point. Type is an optional letter specifying the display format. F displays fixed point notation, E scientific notation, and G is the general format which chooses automatically between E and F. For example, we can display elastic modulus E in scientific notation with 2 decimal places this way. Second moment of area can be displayed using fixed point notation like this. So let's combine these 3 variables and display them in a single line. Let's move on to comments. A comment is a part of the code that is not executed by the Python interpreter. We use comments to explain what the code is doing or to temporarily ignore parts of the code. In Python, comments start with a hash sign and continue until the end of the line. To write multi-line comments, you simply start each line with a hash sign. A convenient shortcut in Python to comment out a portion of code is to select the desired lines They can be partially selected and press Ctrl+//. If you use this shortcut on lines that are already commented, they will be uncommented. Now consider the following example. Here, the variable a is first assigned to the value 8 and then reassigned the value 5. When we print a, the output is 5 because the most recent assignment overrides the previous one. If we comment out the second assignment is ignored, so the final value of a is 8. Let's talk about basic data types. Python has several data types, but I'll mention only the most fundamental ones for now. First, we have integers, which are whole numbers. For example, here, number of beams is equal to 6. You wouldn't use decimal numbers to express a quantity of whole objects. Next, we have floats, which represent decimal values. In this case, I've set beam width to 0.3. A string is a sequence of characters and is commonly used to store text, such as names. Strings are declared by enclosing characters in either single or double quotation marks. They can also contain multiple words. Here, I define a UB section name. Finally, we have booleans, which are binary values that can be either true or false. Note that the first letter for true or false must be capitalized. Booleans are often used in conditional statements, such as if statements, which we'll see in the next videos. Here, I'm using a flag isSteel to indicate that the material is steel. Let's print each of these variables using f-strings. To show the actual data type of the variable, we can use the inbuilt type function and get the name property of the returned object. Don't worry about remembering this, it's just to visualize the data type for you. Remember that if you try to carry out a mathematical operation on a string, like addition, it'll result in an error. You might wonder why. After all, it looks like a number. The reason is that when we declare a variable like this, the value is enclosed in quotation marks, so Python treats it as a string, not a float or an integer. Because of this, we cannot perform mathematical operations on it unless we first convert it to a numeric type. This brings me to type conversion, the ability to change data types in Python. For example, we might want to convert a float to an integer or to a string. We can do this using built-in conversion functions. Let's define a variable var equals 3.5. This is clearly a float as it has a decimal number. To convert it to an integer, we use the int function and place the value inside a parenthesis and assign to a new variable new int1. When we print it, we can see that its value has become 3, not 4 as we'd expect. This is because when converting a float to an integer, Python truncates the decimal part. It does not round to the nearest number. We can also check that the variable's type is now indeed an int using the approach from the previous cell. To round the float, we can use the inbuilt function round, like this. Let's print it. Now, new int2 value is 4. To convert a value to a string, we use the str function. When printing new str, we can see that it is a string. Finally, we can convert a variable to a float using the float function. Naturally, this won't change the initial variable, which was a float already. Finally, let's talk about expressions. Expressions use standard mathematical operators to carry out calculations, which produce a new value. You can see tabulated operators here. These include addition, subtraction, multiplication, and division. Pretty straightforward, so I won't dwell on them much. You can use these operators with variables or directly with numbers. For example, here I'm calculating the average value between a, b, and c. You can see I used a mix of variables A, B, C, and the number 3. One important note: for exponentiation, we use a double asterisk, not the caret symbol. So to calculate 3 squared, we write 3 double asterisk 2. The quotient and remainder operators appear less often in structural calculations, but let me explain them briefly for completeness. The quotient operator, also called integer division or floor division, is written with 2 forward slashes. It returns only the whole number part of a division, discarding any remainder. Integer division of 5 by 2 gives 2, because you're taking the whole number part of 2.5. The modulus operator, percent symbol, gives you the remainder after integer division. For 5 modulo 2, the remainder is 1, because 2 goes into 5 twice with 1 left over. The concepts we covered here will constitute most of your code and should be enough already to get you going with simple structural calculations. Let's finish this video with a practical example: the design of an RC sections reinforcement. We have an 8-meter long concrete beam with a uniformly distributed load of 50 kN per meter. The beam width B is 450 mm and the effective depth of D is 550 mm. Concrete strength is 30 megapascals, whilst reinforcement is 500 megapascals. To calculate it, I will use the rectangular stress block approach according to Eurocode 2 with a British annex, but feel free to apply the method used in your country. In this approach, we assume a linear strain distribution. In reality, concrete stresses are nonlinear and spread over the full compressive depth x. However, for design purposes, we can simplify this by assuming a rectangular stress distribution acting over a reduced depth of 0.x. From this, we can get the resulting forces to calculate the required area of reinforcement. The code doesn't actually provide the equations to solve this explicitly, but you can derive them by hand. To save you time and focus on coding, I've copied all the required formulae for your reference. This is the familiar equation for maximum bending moment for a simply supported beam under UDL. Next, we have an equation for design yield strength of reinforcement. This is an equation for non-dimensionalized moment K. We limit it to 0.167, which corresponds to a ratio of x over d equals 0.45 to ensure a ductile section. Otherwise, compression reinforcement is needed. Then we can calculate the lever MZ between compressive and tensile forces. From this, we get the required reinforcement area. And finally, we can use trial and error to get the number of bars so that the provided area is greater than the required area. In the code cell below, I've already included the input values. Try to pause the video and complete the calculations by yourself. I'll follow with the solution in a moment. First, we calculate the maximum bending moment. I'll define a variable MED, which is equal to WED times L squared, and divide this by 8. Notice that we square using double asterisk. Let's print the answer using 1 decimal place and fixed point notation. This answer is in kilonewton-meters. Although this is how I want to print it out, I prefer to be consistent with the units in my calculations and use only newtons and meters. So I'll multiply MED by million to get Newton-millimeters and divide the printed number by million to display kilonewton-meters. Next, we can calculate design yield strength. That's simply 500 over 1.15, which, when printed with 1 decimal point, is 434.8 megapascals. The non-dimensionalized moment K is found by dividing the design moment by the beam width B, the squared effective depth D, and the characteristic concrete strength. Let's print its value. It's a small number. I think 4 decimal places should suffice. It equals to 0.098, which is less than 0.167, so that's fine. Lever arm Z is given by this equation. Let's print it with no decimal places, as I'm not interested in lengths below 1 mm. This gives 497 mm. Now we can get our required reinforcement area from this equation. The printed value with no decimal places is 1849 mm squared. Let's try 3b16. Provided reinforcement area is given by number of bars times diameter squared times pi, which is 3.14, over 4. We can print this value with no decimal places. It equals only 603 mm squared. That's way too small. Let's try 4b25 bars. This gives us 1962 mm squared, which is greater than 1849. Great, we solved it! One more thing I'll touch on now is this number 3.14. I don't want to always manually type pi, and it's not even this precise. I'll show you a trick you can do instead. You can import a library called math and replace 3.14 with math.py. This doesn't really change the answer, but can make your life easier. When you print out math.py, you can see that it has much higher precision and you don't have to worry about rounding errors. Hopefully, this example shows you that you can tackle many engineering calculations yourself in Python. Try to apply these concepts to your own project. That's it for this video. See you next time.